Today I am going to talk to you about anomalous resistivity in a plasma. We shall discuss conventional radio frequency conductivity of a plasma. Then I will talk to you about response of a plasma which has a ripple in the density to a radio frequency field, and we will introduce anomalous resistivity, deduce an expression for it, and then we will mention what are the causes that can give rise to density fluctuations, and I would like to mention a few things about magnetized plasmas, because we have discussed the kinetic theory of electrostatic waves in unmagnetized plasmas, but most plasmas are magnetized, and hence I should talk something about magnetized plasmas, though without giving a detailed derivation of susceptibility. So, let me, for today's presentation I would like you to refer to one paper and one book. One is by Kruger and Dawson. This is an old paper, and there are a lot of references cited in that paper that are relevant for today's discussion. And then there is a book by Kruger, The Physics of Laser Plasma Interaction, published in 1988. Well, let me briefly formulate the problem. The problem is that suppose I have a plasma, and if I apply a radio frequency field to the plasma, the electric field may be oscillating. Suppose the electric field I subject to the plasma is, suppose Z, and amplitude is A exponential minus I omega t. It may have a Z dependence also, but that Z dependence I am considering for the moment to be weak. Maybe if you like, you can have this, suppose Kz also here. But actually I would like to keep this general, because if I specify my Z dependence like this, then this means the electric field is corresponding to a longitudinal wave, because the electric field in the same direction as Z variation. But in general, a plasma could have an EM wave like this E that can have electric field in the Z direction, but the phase variation may be in the X direction, for instance. So, this is a transverse electromagnetic wave. The wave is traveling in X direction, but the field is polarized in the Z direction. So, this is the electrostatic wave, and this is the EM wave, electromagnetic wave. So, rather than specifying the dependence of space on space for E, I will simply say that I am considering a case where E is equal to, say, Z cap A exponential minus I omega t. But in the system has a density, plasma has a density, equilibrium density is suppose N00 plus there is a ripple in the density. I will call this as NQ, the density ripple, which I will write down NQ as some amplitude N0Q exponential of IQ Z, and I will presume for the sake of simplicity that Q is much bigger than K. So, the dependence on space of current etc. that are produced is primarily coming because of NQ rather than because of E, but the time dependence is coming from the electric field. So, my issue is that if I have an electric field in a system like this, then the plasma will respond by creating a current in the system, and normally we solve the fluid equation which says that m delta V by delta T plus V dot del V is equal to minus E minus m nu V. This is the collisional momentum loss per second. This is the momentum electron gains from the electric field, where minus E is the electron charge, m is the electron mass, and this is the dV by dt, rate of change of velocity. So, what we do? We normally write V as A exponential minus I omega t, because of the electric field having time dependence like this. We write like this and linearize this equation and solve it. We obtain V is equal to E upon m I omega plus I nu. I can write this in two parts. Rationalize this, it becomes E upon m nu square plus omega square. Actually minus times will be here, and you will get nu plus I omega into E. Now, this equation tells you that V has a part in phase with the electric field because of nu, because the real part of nu, but then there is a part of velocity which is out of phase by pi by 2 because of this I term. And if you calculate the power dissipation per second, or energy dissipation per second per particle, then we have mentioned this earlier, is equal to the electric force on the electron is minus E dot the displacement of the electron per second. So, this is the energy dissipation by the wave on the electron per second, where it is implied the real part of the first term and real part of the second term to be multiplied, and which turns out to be half complex conjugate of the real part. So, this is the real part of this product if you take, where a star represents the complex conjugate, then power dissipation you get, and this is proportional to nu. That is why this nu part is called resistive part of conductivity or mobility, and omega is called the reactive part. So, if my plasma were of uniform density, I will get J is equal to minus N0 E V, and that will give me two terms here. One will give me N0 E square upon m nu square plus omega square into nu. Sorry, this quantity is J into E, and another part would be minus, rather plus N0 E I omega upon m nu square plus omega square into E. This is called the resistive part of this whole coefficient. If I take E common, then the total expression is called conductivity. So, let me write conductivity of a plasma N0 E square upon m nu square plus omega square into nu plus I omega. This part of conductivity, real part, is called resistive part, and this imaginary part is called a reactive part or inductive part. Usually in plasmas, nu is very small as compared to the applied frequency, because you apply frequencies, high frequencies, and their nu is very small. So, basically resistive part is equal to n0 E square nu upon m omega square. So, rather than calling this entire quantity as the resistive part of conductivity, we call nu is simply resistivity in layman's, or rather in general usage. So, nu is a manifestation, or mu is representative of resistive part. So, that is the quantity effective nu you have to define. Now, in a collisional plasma, electrons suffer collisions with ions or neutral atoms, and if the plasma is strongly ionized, then there are no neutral atoms. So, nu is primarily due to electron ion collisions. And as you are familiar that this collision frequency scales as minus 3/2 power of electron temperature. So, in a hot plasma this is a small quantity. So, waves are weakly damped via collisions in a hot plasma. However, experiments have found that there are waves that are strongly absorbed. So, what is going on? It has been found that the presence of a wave gives rise to density fluctuations, and whenever there is a density fluctuation in a plasma, it gives rise to a strong absorption of waves. So, now let us try to understand what is the mechanism of collisionless absorption of waves. First, let me give rise to a physical picture what is really happening here. Suppose I have an electric field that I apply. This electric field has a omega frequency and wave number nearly 0 or tiny. Then this wave will immediately produce oscillatory velocity of electrons at frequency omega and wave number nearly 0. As soon as this velocity is produced, this will give rise to a current which will be at frequency omega, wave number 0, plus additional current will be produced because of density fluctuation. That will be because J is equal to minus N0 E V. N0 has two parts, N0 0 part plus NQ part E V, and I am taking omega 0. So, whenever you multiply this NQ with this, you will produce a current at frequency omega and wave number q. This part of current will produce an electric field or potential at omega and q, and this will produce an oscillatory velocity of electrons at omega and q. So, what will happen? If I substitute this V omega q and multiply this by NQ, rather, so this V omega 0 will be actually, now you have additional velocity V omega q. So, the product of this NQ with this V omega q, if you take the complex conjugate, it will give rise to, so this term and this term together will produce current at omega frequency and wave number 0. So, there are two sources to produce current at omega frequency, at the frequency of the wave and wave number of the wave, omega frequency and 0 wave number. One is the product of N00 and V omega 0. This product will give rise to J omega 0, and then this new product will be there. This term will be there even if there were no density fluctuation in the system, density oscillation in the system. But this is the new term that will appear only when NQ is finite. So, whenever there is a density ripple in the system, your current will have additional term. And what can happen? This electric field or potential that you have at omega frequency in q wave vector, if it is such that omega is of the order of kV thermal, QV thermal, in that case this will be heavily Landau damped and it will have a finite imaginary part in its response. So, V omega q will not be in the same phase as the E omega q, but because of the Landau damping term, Landau resonance term or Cherenkov resonance term, it will have a part out of in phase with the electric field, not pi by 2 out of phase, and that gives rise to J which is in phase with the electric field. Otherwise, because of these two terms, if there are no collisions, then J and E are out of phase by pi by 2. But this product, because of this resonance, will have a damping term. So, physically what is happening? That whenever you launch an electromagnetic wave of frequency omega into a plasma, it produces in a ripple density plasma a quasi electric field at frequency omega and q wave vector, and that electric field damps the or takes a feeds energy into the electrons by Landau damping. So, this is a quasi mode which is Landau damped. So, I will call this as Landau damped quasi mode, and that gives rise to effective collisions or effective resistivity in the plasma. So, I would like to make a simple calculation for this, and then I will indicate if you permit finite wave numbers what will happen. It is a trivial extension beyond that. So, let me proceed step by step. Let me redefine the problem. I am considering a plasma subjected to an electric field E is equal to say z cap A exponential minus I omega t, and the plasma has a density n0 is equal to n00 plus n q exponential of I q z. Well, in proceeding further, I would like to remind you of one complex number identity, that whenever you are encountered with numbers like A, which is a complex number, and another complex number B, then the real part of A into real part of B is identically equal to half the real part of A dot B plus A star dot B or A dot B star, either of the you can put a star on either A or B, not on both. You can prove it. So, what I am expecting now, that as a consequence of this electric field, the electrons acquire a velocity v at omega frequency, and that would be equal to E upon m I omega. This is I am getting from a collisionless equation of motion, and you may just check it, m delta v by delta t is equal to minus E. This is the equation I am solving by replacing delta delta t by minus I omega, you get this result. So, this electric field quickly gives rise to this velocity. Now, if I substitute this in this expression for current density J, which is equal to minus the electron density into V E V omega. I think it will be better if I put a subscript 0 also here, because wave number I am taking to be 0 here, there is no space dependence. So, it will produce, this product will have two terms. One is n0 0 e v omega 0 and with a negative sign, another will be minus n q e v omega 0. Now, please remember, I have to multiply the real part of this quantity. Density is a physical observable, it cannot be complex. I have written in a complex notation implying that a real part of this quantity is implied. Similarly, v omega 0 is also a physical quantity which is the real part of the complex number. So, here what I have to do, a real part of this is to be multiplied with the real part of this, and using this identity I have to put a half in there. So, you are creating a wave of frequency omega, a current of frequency omega and wave number q, because the two exponential, one exponential of electric field is multiplied with the exponential here. So, when you multiply the two, this quantity, this product will go as exponential minus I omega t minus q z. So, this will give rise to a current at frequency omega and wave number 0, whereas this will give rise to a current at frequency omega and wave number q. So, let me call this current. So, I will write down J is equal to J at omega and frequency 0, wave number 0 because of this term, plus J at omega and q, and this is the term which goes as exponential minus I omega t minus q z. So, there are two terms produced. Now, this is the term that will produce an electric field at omega frequency q wave vector, and because this, let us look at the direction of this. This j I have taken to be in the direction of v omega 0, which is in the z direction, and its q is space variation is also in the z direction. This is called longitudinal current. Longitudinal current, and whenever you produce a longitudinal current, it will give rise to density oscillations at omega frequency q wave vector. So, let me calculate the density oscillations at omega frequency q wave vector. So, I say that the equation of continuity is delta n by delta t plus divergence of n v equal to 0. I say that my n is equal to n 0 that was earlier, or n 0 0 plus n q that was there, plus you have produced an additional density oscillation at frequency omega and wave number q because of this current. So, I want to calculate the modified density, this term. So, I put this in here and equate or retain here also the product that has omega frequency and q wave vector. So, this equation will give me delta delta t of n omega q plus del of n has these many terms and v has omega 0 term. So, I need a n q here and with v omega 0, so that this product has a frequency omega and wave number q, and half will come because it is a product of two complex real parts of two complex quantities. So, I will put half here. Well, this I call as the nonlinear part of omega q. Why nonlinear? Because there is no velocity here at omega frequency in q wave number. This omega 0 is produced by the original electric field of omega frequency, but the quasi field that is produced by this nonlinear current is not included in here. So, I will call this nonlinear density perturbation. Replace this by minus I omega and this as I q, and which is in the z direction. Simplify this, you will get the density perturbation n omega q nonlinear is equal to q dot v omega 0 divided by twice omega from here into n q. So, it is a simple expression. We got the density perturbation, but as I am saying that density perturbation will also produce a potential perturbation phi at omega k will be produced, because del square phi from the Poisson equation is equal to epsilon 0 if I multiply here. This is equal to density perturbation of electrons at omega k, omega q. Now, whenever you are producing a potential perturbation like at omega frequency q wave vector, this will also produce a density perturbation. Please note that density perturbation n omega q nonlinear is caused by the electric field that you have applied externally, but this is the potential of the quasi field that is generated inside. This will also produce a density perturbation. So, I write n omega q as n omega q linear, which is produced by phi omega q plus n omega q nonlinear, which is produced by the pump wave, which is the outside wave. And from our theory of Landau damping, we have learnt, forget all this, that if there is a plasma wave in a system of frequency omega and wave number q, then the density perturbation is related to that, and that is given by this expression n omega q is equal to q square epsilon 0 upon charge of the magnitude of electron charge into susceptibility at frequency omega and wave number k into phi at omega, sorry, q here, phi at omega q. And all the information about kinetic effects is contained in the susceptibility. So, I do not have to solve the velocity equation, I can simply write down, because I am familiar with my theory of plasma waves, kinetic theory of plasma wave. So, I can always write down the density perturbation caused by this intermediate or quasi potential that is created because of this charge variations. So, I substitute this in here, then this equation takes the following form. So, this gives me phi omega k, phi at omega q turns out to be simply equal to, just substitute it here, and you will get this is equal to minus E n q divided by 2 epsilon 0 q square into q dot v omega comma 0. I am simply getting this result divided by omega into epsilon at omega k q, where I will write down the values of epsilon and chi in a minute. This is the total expression I get for the intrinsic of or quasi potential or quasi mode is called the potential of the quasi mode, or this is the Poisson equation or first Maxwell's equation. Now here epsilon is one plus chi at omega, chi electron susceptibility at omega q, and chi e at omega q I had written in my last lecture as 2 omega p square upon k square V thermal square, k is actually q here, into 1 plus omega upon q V thermal z function of omega upon q V thermal. So, this has imaginary part, and hence this epsilon will have an imaginary part, and consequently phi omega q will also have some imaginary part in the denominator. Now, what is the consequence of this phi omega q? This self field will give rise to oscillatory electron velocity. Phi omega q gives rise to oscillatory velocity v omega q. So, I solve the equation of motion for electrons, which is m delta delta t of v at omega q is equal to the electric force minus E, and electric field is grad phi with a negative sign. So, grad phi of omega q. Just simplify this. Well, to be rigorous, I should solve the Vlasov equation to obtain v omega q in terms of phi omega q. But if omega upon q V thermal is significantly greater than 1, I can still approximately solve the equation of motion, and the result is quite accurate. So, in that limit you simplify this by replacing this by I q and this replacing this by minus I omega, and you will get v omega q is equal to minus E q phi omega q upon m omega. You may note that these equations are really very simple equations, though I am using a number of them. 4 or 5 equations I am using, and I am also using a borrowing an expression from kinetic theory for electron susceptibility. But then in terms of susceptibility, one can easily write phi omega q that I did earlier, and using phi omega q I can write on the electron velocity. Now, I am ready to write my current density. My goal was to find current density at omega frequency and wave number 0. So, I can simply write down J at omega and wave number 0. How much is this? Because this is the frequency of the applied electric field, and this is the wave number of the applied electric field. This will be how much? There will be 2 terms. One is n00 E V at omega 0, and then there will be a term minus nq star I have to take, because I want to cancel the omega q here, because when I put a complex conjugate here, then exponential I q z from here and exponential minus I q z from here, they will cancel each other. So, z dependence is gone. So, this is the density perturbation present in the system. This is the oscillatory velocity produced by the quasi mode that is excited by the nonlinear interaction of the density perturbation and the oscillatory velocity due to the incident electric field. So, now let me substitute the expression for V omega q, and when you do this algebra, you will get this expression turns out to be the same as this n00 E V omega 0 outside. Inside you will get a term 1 plus nq square upon n00 square multiplied by omega p square upon 4 omega square and epsilon at omega q. This is the beauty here. The physics has come out with some clarity here, that epsilon, which is responsible for resonant wave particle interaction through Landau damping, gives you an imaginary part here. Otherwise, this V omega 0 is out of phase from this j omega with the electric field. Let me remind you, V omega 0 we had written is simply equal to, it was E upon m I omega. So, this is out of phase by pi by 2 from the electric field. Let me substitute this here. So, you will get J at omega 0 is equal to the classical conductivity, which is equal to minus n00 E upon m I omega and E square upon omega into E. But besides this, there is a factor here, 1 plus this factor, and imaginary part of this is equivalent to nu upon omega. So, we have got resistivity here through this epsilon term. Now, let me talk about this epsilon term. Epsilon omega k is called the plasma permittivity, omega q, which is approximately equal to, for omega significantly bigger than q into V thermal, this is nearly equal to minus omega 1 minus omega p square by omega square plus I root pi 2 omega p square upon q square V thermal square into omega upon q V thermal into exponential of minus omega square upon q square V thermal square. So, what you are getting is 1 upon epsilon in the denominator. If omega were very close to omega p, then this is nearly 0, and the second term is purely imaginary. So, there is a huge resistivity. On the other hand, if omega is off from omega p, suppose omega is much bigger than omega p, this term is simply unity, but still the imaginary part is significant and it will be important. So, contribution to resistivity will come when omega square upon k square V thermal square is not too large, because if it is too large, then this exponential term will vanish, will be tiny, and when omega by q square V thermal square, suppose like it is like 10, not 100, then exponential minus 10 is significant still. So, when this quantity is not too large, epsilon has significant imaginary part and gives rise to anomalous resistivity. Let me define effective collision frequency. If you compare this expression for current density from the one that I had derived in a collisional plasma, then nu upon omega, effective collision frequency nu star I will call it, is equal to nq square upon n00 square into omega p square upon 4 omega square, and I should take the imaginary part of 1 upon epsilon. This is what I need. So, if I write down epsilon is equal to epsilon real plus I times epsilon I refers here to imaginary part, R refers here to real part of epsilon, then imaginary part of, I think it is minus 1 upon imaginary part. Let me just check the expression for conductivity that I had derived earlier. It was minus, this is effective, this is minus. So, imaginary part of 1 upon epsilon is, rationalize this, epsilon r square plus epsilon I square, and epsilon I will be up with a negative sign. So, effective collision frequency that you are getting, this is also called resistivity, upon omega is equal to nq square upon n00 square into omega p square upon 4 omega square into epsilon I upon epsilon r square plus epsilon I square. This is a very neat expression and valid quite accurately for resistivity, anomalous resistivity of the plasma. There were no collisions. Just because of Landau damping, epsilon I is finite, and I have given the expression for epsilon I also. So, this is an important expression. It is very large when omega is close to omega p. So, when your high frequency wave that you are launching from outside has a frequency close to omega p, then resistivity caused by the density fluctuation could be very large. Now, a word about how are you going to create these density ripples in the system. These density ripples may not be static in time, they may have a slow variation in time. So, rather than having n0 as n00 plus nq, you may have n at omega frequency and q wave vector. This may be a density fluctuation due to a sound wave or ion cyclotron wave or even plasma wave. So, any wave present in the system will give rise to this, and what you require that when you are launching and the wave that you are having launching from outside may have a frequency omega and wave number k, may not have k equal to 0. So, in general, if your external field is at omega frequency wave number k, you will have a strong damping whenever omega plus capital omega and k plus q, because the intermediate field that you will produce by nonlinear mixing or nonlinear interaction, the current rather that you will produce J nonlinear will be at this frequency and this wave number. So, the electric field that you will produce in the intermediate case will be at a frequency omega plus capital omega and k plus q. Whenever they are in Cherenkov resonance in the vicinity. So, whenever omega plus omega upon K plus Q is of the order of V thermal, not exactly equal to V thermal, maybe 2 times V thermal, 3 times V thermal, it is all right. They will give rise to a strong these give rise to a strong anomalous resistivity. So, what you require? The presence of a low frequency mode in the system, and now you may ask a question that the mode may not have a single frequency, it may be many frequency modes or many wave numbers. That is certainly possible. So, you have to add up, like the expression for anomalous resistivity contained NQ modulus square, you have to really sum over all such modes, and that is not difficult to do, and that actually becomes the problem of turbulence theory. A system in which there are many waves of many wave numbers present simultaneously, and you want to examine the response of another wave or electric field of the another wave, then you have to consider the simultaneous interaction with the oscillatory velocity due to the incident wave, with the density fluctuations due to all these waves. And this has been a major research area over the last several decades. And one of the most fascinating manifestation of anomalous resistivity has been in fusion devices. In laser plasma interaction, for instance, laser produced plasmas, people have seen a lot of ion acoustic turbulence, and that is responsible for anomalous resistivity. Even in the ionosphere, in the F region of the ionosphere, I mentioned to you that we see spread F instability, which gives rise to low frequency, short wavelength density fluctuations. So, that also gives rise to anomalous resistivity, but these are important when the wave number of the perturbation has to be such that Q has to be such that omega upon Q has to be close to V thermal. That is the crucial aspect. So, all density fluctuations are not going to play an important role in anomalous resistivity. Only those ones that satisfy this condition, this sort of condition, they are going to play a role. It is a very crucial condition, and I think plasma is very rich in waves, especially if there is a magnetic field in the system. Then you can get all sorts of instabilities. Drift waves, for instance, are a major instability in plasmas, and they can provide anomalous resistivity. Not only resistivity, they can also provide anomalous diffusion, anomalous conduction in the plasma. So, I think before I close today, I would like to mention a word about how would you study the response of a magnetized plasma to electrostatic waves. So, a word about electrostatic waves in a magnetized plasma. I am not giving any derivation here, but let me mention 2-3 things. Consider a plasma with magnetic field in the z direction, and if you introduce any plasma in this which is hot into this magnetic field, then the electrons will gyrate like this and ions will gyrate like this in larger orbits. So, this is ion motion, this is electron motion. So, this is electrons and ions. They will gyrate about the lines of force. And if you are launching a wave in the system, suppose a wave is going in the system with k vector here, then this wave will have electric fields with these kind of variations. Now, these gyrotonic particles, when see an electric field, as I mentioned earlier, suppose I consider a potential phi which is equal to A exponential minus I omega t minus kxx minus kzz. Suppose this is a kind of potential of an electrostatic wave I consider, because this x is not constant, x is particle, x quantity gyrating, is changing. So, typically I would write that x is equal to some guiding center plus V perp by rho or cos, or I think sin omega ct. There is oscillation like this. Kz also, z also is not constant. This z of the particle is equal to initial value of z plus Vz into t. So, there is a time dependence arising through x and time dependence arising through z here. So, effective frequency of the potential as seen by the particles is different, and one can employ, I think I gave this expression, that whenever you have exponential, in the exponential a sine function, you can use a Bessel function identity, and the identity was like this, that exponential of I alpha sin theta is equal to summation over n j n of alpha exponential of I n theta. So, when you solve the Vlasov equation, keeping in view that your potential has x and z dependence, and that has to be taken into consideration, and then solve the Vlasov equation for perturbed distribution function, what you get an expression for susceptibility which is equal to 2 omega p square by omega k square v thermal square 1 plus omega upon k v thermal kz v thermal. This I am writing for a uniform plasma, this multiplied by summation over n arising because of this, and there is a term here z function of omega minus n omega c upon k z v thermal of electrons into a modified Bessel function of order n argument b exponential minus b. This is called modified Bessel function, which is tabulated, and b is a quantity that is responsible for k perp rho square by 2, and rho is equal to thermal velocity of electrons upon cyclotron frequency of electrons. Cyclotron frequency is EBS upon m. Thermal velocity is the same as defined before. Rho is the Larmor radius. So, this is the kind of expression you get, which is significant modification over the expression for chi that I gave you earlier. Now, you may note here that the argument of this depends on omega minus n omega c, and you can get very strong large imaginary parts of the z function whenever omega minus n omega c is small, is comparable to kzv thermal or smaller, because this is the same plasma dispersion function as before. So, the argument of the depends on omega minus n omega c. So, you get resonances around omega equal to n omega c. Well, your dispersion relation for the electrostatic wave is 1 plus chi e plus similar expression for chi I equal to 0. This is the general dispersion relation, but as you see here, there are many terms in here, and consequently this gives rise to many modes. And one of the interesting modes is, a category of modes is the one whose frequency is around n omega c and b is bigger than 1. k per rho is bigger than 1. So those special kind of modes are called Bernstein waves. Let me just write this. So they are called electron Bernstein waves. For these waves, chi I can be taken to be infinite. I am talking of waves of frequencies around n omega c. You can forget this, and when you simplify this expression, omega turns out to be around some integer multiple of omega ci into 1 plus I n exponential minus b divided by some factor here. I forget the factor, but of this order unity. So this is this omega c rather, not ci, this is omega c. You get this a very special category of modes with k per rho greater than of the order of unity, very short wavelength or large k per modes. These modes propagate primarily perpendicular to the line of force. If magnetic field is here, these waves travel like this, almost perpendicular. And similarly, magnetized plasmas offer iron Bernstein waves of frequencies close to multiples of iron cyclotron frequency. These modes can be driven unstable if there are currents in the system, and people have observed in beam plasma systems current driven or electron beam driven Bernstein waves, electron Bernstein waves, and if there is a lot of turbulence or there are some high amplitude perturbation density fluctuation, then they can give rise to anomalous resistivity as well. So today we have learned that presence of fluctuations in the system, density oscillation in the system, gives rise to absorption of waves of high frequency. I think that is a very frontline area of current research as well, and a lot of new situations are emerging where waves are unstable and you are having a lot of anomalous absorption of waves. And I think I close at this point. Thank you for your attention.